In this video, we will introduce the concept of the inverse of a matrix, and without a doubt, this is probably the most important operation or concept that involves a matrix that we will use, right? But in order to get to the idea of the inverse, we need to define a few more things. In particular, we need to define another special matrix. I mean, you might even say this is a super special matrix. And then based on that, we will look at some of its properties, and then we will then define the inverse. So let's get started. So recall a diagonal matrix is a square matrix, right? So is a square matrix such that the let me say it this way, the aij's are equal to 0 whenever I is not equal to j, right? So again, remember what this is saying for a diagonal matrix is that for elements that are not on the main diagonal, and those are the elements where the row index and the column index are different, like 3, 5 or 1, 7, all those entries have to be equal to 0. So what this implies is that the only entries in a diagonal matrix that can be non-zero are the entries on the main diagonal, right? Now, but even so, that still leaves a wide. I mean, it's an infinite set of possibilities because you can put any number on the main diagonal, and then zeros not on the main diagonal. However, if we add a certain property that says what non-zero numbers have to be on the main diagonal, then we're going to get a special matrix that has some really important properties. So in addition to saying what has to happen when you're not on the main diagonal, if we put a restriction, a special restriction on the entries that have to be or that are on the main diagonal, then this is the matrix that we're about to define, and we'll see why it's significant. So if A is a matrix that looks like this, and let's say an n by n, such that the aij's are defined in this way. And again, it's going to be piecewise, and it's going to be 0 for entries that are not on the main diagonal, so we're going to utilize this, but now we're going to specify what has to be on the main diagonal. That's when I is equal to j, and we're going to require that those entries be equal to 1, right? A nice binary definition, right? So the entries are going to be 0 if they are not on the main diagonal, and they are going to be 1 if they are on the main diagonal, right? So let's write down a couple of these and see what they look like. So like say the 2 by 2, right? So the 2 by 2 matrix that fits this definition will look like this, right? So again, you have 1s on the main diagonal and then 0s everywhere else, right? If we do the 3 by 3, then the pattern becomes even clearer. So 1 0 0 0 1 0 0 0 1, right? Again, because this is so much fun, let's do the 4 by 4, right? So the 4 by 4 diagonal matrix with 1s on the main diagonal looks like this: 1 0 0 0 0 1 0 0 0 0 1 0 0, 0, 0, 1. Right? So just simple matrix, but it has a very significant property. And let's start by illustrating that property in the 2 by 2 case. If I take any 2 by 2 matrix, right? So let's define these two things. So let A be my special diagonal matrix with the ones on it, like this. And let B be any 2 by 2 matrix. So how do I write down any 2 by 2 matrix? Well, I could write it down like this. Just put like generic kind of placeholders in each position, like that, right? But because we have only 4 entries, sometimes, having to write all the subscripts can be a bit tedious. So we can say, okay, well, let's not go to that degree of complexity. Let's make it a little simpler. And then I'm going to say, well, let's cross this out. Say, I don't need all of that. Since I only need 4 entries, I'm going to use this form. A, B, C, D, right? So again, just 4 letters, and then what are the possible values that A, B, C, and D can take on? Well, if we want to um, represent all possible 2 by 2 matrices, then these entries could be any real number, right? In fact, it could be any complex number, but right now we're just working with real numbers like this, right? So this is how I could, if I want to establish a property for all 2 by 2 matrices, then I would work with something like this, right? So what are we going to do with this? Well, we learned about matrix multiplication, right? Let's see what happens if we do the product A, B. All right. So that means I'm going to take my special diagonal matrix that has ones on the main diagonal, and I'm going to multiply what is now any 2 by 2 matrix, right? So A, B, C, D. All right. So again, remember our little rule where we're going to do, row by column, right? So again, I'll write out the terms so we can see what's going on. So if I take the first row and the first column and do that special dot product, I'll have 1 times A, so that's A, plus 0 times C, so that's 0. And then repeat the process. First row, second column, I'll have 1 times B, so that's B, plus 0 times D, so that's plus 0. And then I know I've finished out the column, so then I'll close my square brackets and then move to the second row. So 0 times A plus 1 times C. And then finally, second row, second column, 0 times B, and then plus 1 times D. And look at what we get back. A plus 0 is A, B plus 0 is B, 0 plus C is C, 0 plus D is D. We get back the original matrix B. Interesting. And so that's a B with an exclamation. It's not B factorial, right? So it's like, yeah, we get back B. So we did our matrix multiplication with this special matrix that has ones on the main diagonal and zeros elsewhere. And regardless of what 2 by 2 matrix I use, right? And this is why I wanted to make it general to say whenever I do this type of product, I'm always going to end up with the matrix B that I started with, right? Well, we know and we've seen examples where the product of 2 matrices, the answer could very well depend on the order in which we do the multiplication. Let's say I put B first, right? So consider this product, B times A. So if I put my general 2 by 2 matrix there, and then my special this special diagonal matrix with only ones on the main diagonal, let's see what happens when I do the product this way. I'll have A times 1, that's A, plus B times 0, that's 0. Next column, A times 0 is 0, plus B times 1 is B. Now move to the second row, C times 1 is C, plus D times 0 is 0. And then finally, second row, second column, C times 0 is 0, and then plus D times 1 is D. And look at what we get back. A, B, C, D. So we still end up with our matrix B. So whether, now let me introduce a couple phrases. So basically I'm taking the matrix B and I am multiplying it by A. And the multiplication here, I either put A first. This is an example of what we call pre-multiplication by A, because we put A as the first factor. So it's pre. So this is pre-multiplication by A. And this one where it's after, where it's like after the multiplication sign, this is post. So this is post multiplication by A, right? And whether we do pre or post, look at what happens. B is unchanged, right? That's pretty significant. And to give you an analogy, here is the analogy in terms of real numbers, right? So in fact, let me do this in a different color. So if x is any real number, we know that if I take 1 times x, I'm going to get back x. And similarly, if I take x times 1, I'm going to get back x. So it seems like this kind of multiplicative property that the number 1 has, the analogy for matrices is where this special diagonal matrix, it has the exact same property, but for matrices, right? And because of that, we give it an important name. Now, the important name, for instance, the number 1 is called the multiplicative identity, right? So the number 1, so 1, because of this fact, is called the multiplicative identity, meaning whenever you multiply by this special number, it doesn't change anything. So it just, whatever you multiply it by, it just gives you back the same thing. And that's the identity. In other words, it doesn't change the object that it's multiplying. Same thing, this special matrix, the 1, 0, 0, 1, with respect to 2 by 2 matrices, I could take any 2 by 2 matrix, do either my pre or post multiplication, and it will not affect the other matrix. In this case, I'm calling it B. So we're gonna essentially steal this concept from the algebra of numbers and apply it to the algebra of matrices. So in general, we refer to this special matrix. So again, so the matrices, or let's say the diagonal matrices, with ones on the main diagonal, right? Those matrices are referred to as the multiplicative identity, and they even have a special notation for it, right? So the diagonal matrices with ones on the main diagonal are known as multiplicative identities. Now, the reason I'm pluralizing it is because you have one for the 2 by 2s, you have one for the 3 by 3s, 4 by 4s, and so forth. So they're all identity matrices, they just have different dimensions, right? So they're known as multiplicative identities. And they even have a special notation, right? Just like how the number 1 has this, kind of unit presence associated with it. Well, we have a nice notation for inverses. What we're going to use is we're going to use the letter I, right, as the abbreviation for identity. But since we're using it to name a matrix, we have to follow our naming convention and make it uppercase I. And then since, again, I want to convey the sense that we have this concept for all square matrices, right? We want to identify what the dimension is. So we know it has to be square because I said it's diagonal, right? So we know it has to be square. So what we do is we just use a single n here, and that n is understood to be the number of rows and columns. So I sub n. Again, I'm going to restate the definition that I did earlier, but now this is the special notation that we were going to use henceforth for the n by n identity matrix. And again, it's going to be defined this way, where you have ones on the main diagonal, so that's when your I is equal to j, and then 0 otherwise, right? So now, going back to that little list of examples that I gave, now I can add this special name to it. Technically speaking, there is an I1, kind of a strange idea of having just one row and one column, but yeah, it looks like this, right? And that kind of looks like the number 1, except we're putting square brackets around it. It is possible to have a matrix that has just one row and one column. Sometimes it's considered a trivial matrix, but then if I have 2 rows and 2 columns, then this is the identity matrix that we established for the 2 by 2s earlier. And then this pattern continues just by increasing the number of rows and columns. So I3 is that 1, 0, 0 matrix, 0, 1, 0, and then 0, 0, 1, right? Etc. Right? And they all have this property. So for instance, for all 3 by 3 matrices, this will be the multiplicative identity. All right? So that's the first thing that we need to establish before we start talking about the inverse. Well, now that we've established it, let's have the conversation about the inverse. So I'm going to use the concept of real numbers again to give you an idea as to why the inverse of a matrix is defined in a particular way. So I'm going to switch back to red. This is like we're going back in time to algebra, but we're being a lot more precise in how we define things. Now, so we have the concept of the number 1. Now, again, for x, any real number that's not equal to 0, if I give you that value x and ask you, what could I multiply this x by in order to get the multiplicative identity? Or if I wanted to say, what could I take x times what, again, would give me the multiplicative identity. So whatever this special number is, it's actually called the multiplicative inverse of x. And for real numbers, we know what we would need to do. We would need to multiply by the reciprocal of x. And that's why we have to specify that x can't be 0. 0 does not have a reciprocal, right? So this special thing right here, so the question mark is actually equal to 1 over x, which again is going to be another real number. As long as I don't try to take the reciprocal of 0, The reciprocal of any other real number is another real number, right? So what we say is that, again, for all real numbers that are not equal to 0, x and 1 over x are what we call multiplicative inverses. So these are called multiplicative inverses, right? And again, what is the definition of a multiplicative inverse? Well, it's two numbers, or technically what I should say is x is the multiplicative inverse of 1 over x, and 1 over x is the multiplicative inverse of x. And the property that kind of links them together is the fact that if I take a number and its multiplicative inverse and multiply it either this way or this way, I get the multiplicative identity. So what numbers, when I multiply them, will give me 1, right? And you can think about how important that concept is in solving lots of equations, like linear equations. Again, just to give you a sense of how it works. Let's say I have the equation, again, and I'm going to keep it general. Let's say I have the equation a times y is equal to b, right? And a is not equal to 0. And if I say to solve this equation for y, I think, probably 9 out of 10 students will say, yep, I just divide both sides by a. But that's not the precise way to look at it. This is the precise way to look at solving an equation like this. Since the coefficient is not equal to 0, it has a multiplicative inverse. So we're going to multiply both sides by that multiplicative inverse. What is it? It's the reciprocal. So we're going to take 1 over a times y, and whatever I do on that side, I have to do on this side, right? And how does that help? Well, now we use the associative property of multiplication and say, well, I have 3 things that I'm multiplying here, but I am going to choose to multiply the first pair. Why? Because the product of a number and its multiplicative inverse is equal to 1. So that's essentially how you cancel out the a. And again, I'm gaining a greater dislike for the word cancel because it's used, and it's used, it's used with reckless abandon, right? But this becomes a 1, and then this is still y, and over here we still have the reciprocal, 1 over a times b, so it's like this. And then how do we get y? Well, it's because now we've now reduced this factor to the multiplicative identity. So 1 times anything is going to be that same thing. So that's why we're left with just our variable isolated, and then we have this expression over here that we can write as a single fraction, and we get b over a. Very few, if any, students at kind of an elementary algebra level would think through the properties like this. It seems like it's the shortcut, so it's so much easier to say, yeah, let's just divide both sides by a. No, there's a lot more that I think that should be said, at least initially when you're introducing the idea, to say, okay, why can we cancel these things out even though we have 3 factors being multiplied? It's because we have the associative property. Why does it become 1? Well, that's because you're multiplying multiplicative inverses. Why does this stay the same? Well, it's because you're multiplying y by the multiplicative identity. So I don't know, is it too many big words? Is it just much ado about nothing? I would argue not, right? It needs to be said, right? So this all in red here is now our motivation to try to replicate this, but instead of with numbers, do it with matrices, right? So we want to find, now that we have the identity for matrices, right? These I's, we go back up so we can see them in all their glory. We have all these I's, right? So we know what's on this side. The question now is what goes here? What is the question mark going to look like for matrices, right? So let's illustrate this concept for a 2 by 2, right? It's easier to kind of see, to get a handle for things with the 2 by 2, and then we'll be able to do a more sort of a more comprehensive generalization of the property, right? So just as an example, right? So here's the question that we're going to try to answer. So what does this property, right? Property or process, look like for matrices, right? And so the question is, so I'm gonna what I'm gonna do now is pick a sort of generic, not a generic, but just a random 2 by 2 matrix, and ask ourselves, could we find another 2 by 2 matrix that when I multiply those two, I will get the identity, right? So that's what we're gonna try to do. So let's just say, so let A be equal to 1, 2, 1, 1, right? So let's say this is our matrix, right? And now, so our question is this: is there another 2 by 2 matrix? And we don't know what it is, so again, let's just call it B, right? So another 2 by 2 matrix, let's just call it B. Let's take the same generic one, A, B, C, D, such that, right? Now, before I write down what it is I want, again, I'm thinking back to what it was in the algebra of numbers. Now, look up here. This special property, it works regardless of the order in which we multiply. So for instance, if I'm trying to find the multiplicative inverse of a matrix, I could just take the matrix and then try to figure out what the special one would have to be to give the identity. Or I could put the special one before, right? So I'm just going to use the first equation here. We're not going to redo the process because it's pretty much going to be identical, right? So what I'm going to do is, so here is the matrix, the specific matrix that I have, and I'm trying to see if I can find another 2 by 2 matrix that when I multiply them, so here's the equation that we're going to try to work with. So A times B, I would love that to be the 2 by 2 identity. If I could do that, then I have a legitimate case for calling B the multiplicative inverse of A, right? Right? And then we can start naming fancy things, and then doing things with the fancy things that we name. All right. Okay, so let's kind of set it up now. So this is the idea. We would like to find, so this is our question here. We would like to find the matrix B, if possible, that would satisfy this equation, right? And when you look at it, it's a product, and we know how to do a product, right? And presumably we know how to solve equations. So let's see what's going to come out of this. So I have 1, 2, 1, 1. So that's my specific matrix A. And again, this was just a matrix that I picked at random. But now we can't just pick another one at random. We really have to figure out what A, little b, C, and D are, so that when I do this product, I get the identity matrix, right? And then, how do we do this? Well, we're claiming that when we multiply these two, it's going to be equal to the identity, the 2 by 2 identity matrix. We know what has to happen for two matrices to be equal. the dimensions have to be the same, and that's definitely clear. You have a 2 by 2 times a 2 by 2, you'll get another 2 by 2. So that there's no problem there. And the other condition is that the 4 entries that we're going to have on the left hand side will have to equate to the 4 entries on the right hand side in the corresponding positions, right? So let's take what's on the left and write it as a single matrix, set them equal to each other, and see what has to be true about A, B, C, D. Right? So let's do this. So we have, so when I do my, again, row times column calculation on the left, I'll have A and then plus 2C, and then I'll have B plus 2D, and that's going to be the first row. The second row will be A plus C, and the second row, second column is going to be B plus D, right? And that has to be equal to this special 2 by 2 identity matrix. But not only that, we know that the corresponding entries now have to match up. We know that this A plus 2C has to be equal to 1. We know that the B plus 2D has to be equal to 0. I know that the A plus C has to be equal to this 0. And then I know the B plus D has to be equal to 1. So what we actually get are, we get a bunch of equations. In fact, they're linear equations. So let's write them down. So this implies that A plus 2C has to be equal to 1, and then A plus C has to be equal to 0. And it's kind of interesting that here, the equations that I get from this column, they only involve A and C. So it's almost like I could solve this system independently, because this is now a linear system and I can figure out what A and C are. And then look at what happens when I take the entries in the second column. I have, again, 2 equations, 2 unknowns. B plus 2D is equal to 0, and B plus D is equal to 1. Now, these are not difficult to solve. In no way am I going to pretend that these are difficult to solve. But what's really interesting is this. If I write this system in the augmented form, this is what it looks like. 1, 2, and then I have the 1, 0, and then the 1, 1. If I write this system in augmented form, look at what we have. 1, 2, 1, 1. And then we have a 0, 1 there. So it's kind of interesting. Look at how this works out. In order for us to figure out A, B, C, D, we need to solve 2 by 2 linear systems, but the coefficients are identical. Not only that, but look at this. The matrix, remember, we're trying to find the inverse, the multiplicative inverse of this matrix. And these are the entries that end up right here and right here. Interesting. The matrix that we're trying to find the multiplicative inverse of just ends up being our coefficients. And then here's the other remarkable piece. This column, let me scroll back up just a little bit. This column, so the first column in the identity ends up over here, and then the second column in the identity ends up over here. So it's, we went through the actual matrix multiplication, and we applied the property of what it means for matrices to be equal. But it seems like we did a lot when we really don't need to. It seems like whatever matrix we're trying to find the inverse of, it just ends up being the coefficient in these two systems. But then and then I think about how do we solve linear systems, right? We have an elimination process. And that elimination process depends or is geared towards turning this left-hand side into one of our echelon forms, right? But whatever operations I use to turn this into an echelon form will be the exact same operations that are used to turn this into the echelon form, because they're the exact same coefficients. So why do the same thing twice? Why don't we think of a clever way of solving these two linear systems simultaneously? Doesn't that sound cool? We're solving, we're going to solve simultaneous systems simultaneously. And we can do that because the coefficients are identical. So I'm going to write something now down, and it's still going to be augmented, but I'm going to do this. I am going to put this first column here after our little fence, and then put the second column right next to it like this. Because it's almost like I could reduce both of these systems simultaneously, right? So this is not really a formal name, but it's almost like you're doing a double augmentation, where you're augmenting the same coefficients on the left with different b's. So this, you could think of this almost now like as a b1 and a b2. If the coefficients of your system are the same, there's no point in you doing the exact same row operations on this one and then doing it again on this one. If we just do them together and keep track of these columns, then we'll be able to solve both of these equations simultaneously. Okay, so let's see what happens. So let's reduce the left hand side to an RREF, and then I promise you something magical is going to happen to this side. All right, so our goal is to turn this into the RREF, and so let's do our row operation. So I'm going to take negative row 1 added to row 2. That will eliminate this. So the first row stays the same, and then now I'll have a 0 here, and then negative 2 plus 1 is negative 1. But then I have to do it on this side. So I'll have to take negative 1 plus 0, so that's negative 1, and then 0 plus 1, that's 1, right? And now, so we want this leading term to be a positive 1. So let's multiply through by negative 1. I guess we could go a little bit to this side. So if I take negative 1 times row 2, so let me write the new row 2 first. So we will have 0, 1, 1, negative 1. First row stays the same. So I have 1, 2, 1, 0. And now let's, this is almost this is now an REF, but let's go all the way to RREF and eliminate this 2. So let's take negative 2 times row 2 and add that to row 1. So again, second row now stays the same. So we have this. And then let's multiply this by negative 2 and add it to the row above. So this is still a 1. And then I'll have negative 2 plus 2, so that's 0. And great, we have the identity there. Now I have to make sure I do these operations right. So I'm going to take the negative 2 times 1, that's negative 2, plus 1, so that's negative 1. And then negative 2 times a negative 1, that's a positive 2, plus 0, that's 2, right? So what this tells me now is that So let me kind of split this back to where we started. All right, in fact, I'm not even going to split it, but look at where we started. For the column that started with the 1, 0, that would be us solving for A and C. So those values would be right here. So actually, without even having to do much work, I can say that this is A and this is C, right? And then the other column now, the one that started out as the 0, 1, that's the column that we would solve if we were solving for B and D. But having reduced it, I can say that this is B and this is D. So it seems like the matrix that we were trying to find the inverse of, if we augment it with the identity, and we're able to convert it to a RREF where we have every row has a pivot, it seems like what happens on the right hand side is going to be the inverse of the original matrix. So here is my claim, right? It's going to be a pretty bold claim. So here's our claim. So remember, in fact, let me go back up to show you where we started. There's a lot of interesting things that have happened. We have our matrix A, 1, 2, 1, 1, and now I claim that we've found the A, B, C, D that will satisfy this. So I am going to claim that that matrix that's now on the right, or the entries that are on the right, form the inverse of my original matrix. So my claim is this, that the matrix -1, 2, 1, -1 is the multiplicative inverse of our original matrix, which was the 1, 2, 1, 1, right? How do we verify this claim? Well, we do the multiplication. So now that we have what we think is the answer, let's multiply these two matrices both ways, right? Because it has to work both ways for us to call it a multiplicative inverse. So let's take the product of this matrix times this matrix, right? This was our original A. This was the B that we just found. Let's multiply these two and see if we do get the identity. So let's check our claim. So let's do B like this times A, which is the 1, 2, 1, 1, and let's see if the magic happens. So first row, first column is -1 plus 2. Looks good so far. First row, second column, -2 plus 2. Looking great. Second row, first column, 1 minus 1. Man, this is unbelievable. Second row, second column is a 2 minus 1. And this is where I need fireworks, I need confetti, break open the champagne. Yeah, or apple cider, your choice. But this is 1 and 0 and 0 and 1. So it gives us the identity that we want, right? But, hold the bubbly just for a second. We have to make sure that it works if I change the order, right? Because that's what we want from a multiplicative inverse, that it shouldn't matter the order, right? If we want it to look like what it looks like for real numbers, we would want the product, right? In other words, these matrices, and I'm going to, again, use the word cancel out, right? As much as I don't like it. But yeah, they should, or put it this way, this product, if we can indeed say that this is the multiplicative inverse, this product has to reduce to the identity, the 2 by 2 identity. So we have -1 plus 2, so -1 plus 2 looks the same thing right there. And then here we have 2 minus 2, still 0, and then -1 plus 1, still 0, and then 2 minus 1. Now, pop the champagne, right? So we have this, and that's our identity. So we found it. We found the mystical unicorn that is the multiplicative inverse of this matrix, right? So, with that in mind, I am going to, I know this has been quite, I told you it was going to be quite the journey, but hopefully the destination has made it all worthwhile. Let's now write down the formal definition for the inverse of any n by n matrix. So, given an n by n matrix A, if there exists, right? Because we don't know. Like, remember, we had to solve a system or several systems to figure out what this magic thing was. And remember, not every linear system has a solution. So maybe sometimes we're going to try to do this process and we might end up with a contradiction, right? So we have to put this huge and important disclaimer there. So given an n by n matrix A, if there exists an n by n matrix, and we're going to call it B using kind of the same notation that we used earlier. So if there exists an n by n matrix B such that, what do we want? Well, we know what we want. We want the product of A times B and B times A. We want that to be the n by n identity. So if we can find this other mystical unicorn for a given square matrix, right? We say a couple things. We say that this matrix is invertible, right? So we say that A is invertible, and that B is its multiplicative inverse, right? And that B is its multiplicative inverse. And we even have a special notation for it. Of course we do, right? We have a notation for everything, right? We have a notation for notation. So that is its multiplicative inverse. And here's the notation for B. And what we're going to do, again, let me take us back down memory lane. So we had said that 1 over x is the multiplicative inverse of x, provided that x is not 0, right? So we have this. But think of another way that we can write 1 over x. We don't want to have to write 1 over a matrix. And the reason why we don't want that is because this fraction bar here is actually saying division, right? And we don't have the concept of matrix division, right? As far as the arithmetic operations that we have scalar multiplication, matrix multiplication, addition and subtraction. We don't really have division. So we're not going to use this notation in the matrix form. What we're going to do is use this notation with the -1. So the -1 here is telling us, okay, in order to find the multiplicative inverse of a real number, take the reciprocal of it. When we switch over to matrices, the -1, which is what we're going to use, will tell us to find the multiplicative inverse. And the example that we did above gave us kind of a template of how to find it, right? So here's the notation. So we denote, again, if we can find such a B, let me write denote properly. So we denote B by using A inverse, right? So again, so this is going to indicate, this is the notation that we're going to use to represent the multiplicative inverse of an invertible matrix, right? And so we still have a couple things to settle, right? Because there's this if, right? You know, how do we know that there is a multiplicative inverse, right? Well, the process that we just outlined through that example, again, not only is it going to give us the multiplicative inverse when there is one, but if something goes wrong in that process, then we will know that the matrix does not have a multiplicative inverse. So everything is going to be wrapped up. And where are we back? We're right back at our eliminations, right? Can't get rid of them. Gauss, you know, Jordan, everywhere. Okay, so this is a perfect place to stop. And I want you to really think about a lot of what we did today. Maybe go back and try to do the process yourself. Maybe pick another 2x2 matrix and try to do this process and see if you're able to find a multiplicative inverse. And while you do that, I'm going to prep for the next video. See you then.